proposition. Proposition. I'll call it proposition 1. If P is less than or equal to Q, then LP is a subset of what? LQ. Okay, we have, let's look at 3 cases. 3 cases arise. Case 1 is when P is equal. Remember here, P less than or equal to Q, LP is equal to, is a subset of LQ. Here we are assuming that P and Q satisfy that.
Yeah.
That's correct. So case 1 is equal to Q, then the hypothesis is trivially true. Then hope we agree?
Yeah.
Because every set is a subset of itself. Then case 2, what I've looked at as case 2 is the case where P is less than Q, less than plus infinity. Let xn n equals 1 to infinity be in LP. Take it in LP. Our job is to show that it belongs to what? LQ. We show that Sn n equals 1 to infinity belongs to what? LQ. We want to show. It is enough to show that summation n equals 1 to infinity, absolute value of Sn raised to power q is what? Is finite. We can do this, and this is possible because P is strictly less than Q. And not only that, let me call here, say 1. And since Sn n equals 1 to infinity belongs to LP, we easily see that Sn n equals 1 to infinity is what? Is bounded. Is bounded since summation n equals 1 to infinity, absolute value of Sn to the power p finite implies that absolute value of Sn to the power p goes to 0 as what? N goes to infinity, which implies that what? Xn goes to 0 as what? N goes to infinity. Implies that, which in turn implies that what? Sn n equals 1 to infinity is what? Bounded. Since every convergent sequence is what? Is bounded. So Sn is bounded. Since Sn n equals 1 to infinity is bounded, there exists a constant k greater or equal to 0, such that for all n in the set of natural numbers, absolute value of Sn is less than or equal to k. This implies that absolute value of Sn raised to the power q minus p is less than or equal to k raised to the power q minus p. this one
Okay.
will be less than
Yeah,
or equal
yeah.
to this. Of course, the power function is an increasing function. So, okay, this less or equal to this implies this less or equal to that. Good. And Q minus B is positive.
Yes, because Q is bigger than.
So, from 1, so we obtain from 1 that absolute value of Sn to power Q is less than or equal to what? K raised to power Q minus P, the absolute value of Sn to power P. So where is this leading us to? If you see this as a term of a sequence, and this is a term of another sequence, and this is happening for all n in the set of what? Remember, it's for all n greater equal to what? For all n in the set of natural numbers. Okay, let me maintain notation. For all n in the set of what? Natural numbers. So what does this tell us? This is a non-negative term. This is the non-negative term. These are non-negative terms. This is the non-negative. If the series in this converges, this one was converge. Isn't that? So from there, as J tends to infinity, we obtain that, and this is finite.
Yes.
Let me call here 2. Sn in LP implies Sn in what? Provided P is less than what? Is less than Q. This implies, so for P less than Q, both less than between 1 and infinity, we have that LP is a subset of what? LQ. That completes the case 2. Then case 3. If you were watching, you'll find out that the case 3 is already embedded in what we are doing. Somehow, you see this somewhere. Case 3 is when Q is plus infinity.
Okay.
If Q is plus infinity, and P is of course less than, P is between 1 and plus infinity. In that particular case, Xn in LP will mean that what? Xn is what? Bounded.
Okay. Yeah.
Because the summation of this is finite, then this will go to what? The term will go to 0, meaning that Sn converges to 0. And being a convergent sequence, it is what? Bounded. And since it's bounded, Sn belongs to what? L infinity.
Okay.
That's what? That clears the dead case.
Yeah.
You understand? That's it. This is what we are assuming.
Okay.
That Q is plus infinity and P is less than what? Q. So in all, what our conclusion is there? Our conclusion is what? That in all, LP, whenever P is less than or equal to Q, LP is a subset of what? LQ.